Okay, I think we can start. Welcome to the European Non-Associative Algebra seminar. It's a pleasure to introduce the speaker of today, Professor Dietrich Burde from the University of Vienna. The title of his talk is Pre-algebra Structures on Reductive algebras and Etale affine representations. Please, Dietrich.
Welcome to this talk. I have two remarks which I want to say beforehand. First is to thank the organizers for establishing such a seminar, which is really a nice idea. And I'm very grateful that I have the opportunity to speak. And secondly, let me also take the opportunity to remember my student, Wolfgang Muns, who passed away last year unexpectedly. And I want to say a few words that he was very active in our group for many years in this topic, and that we miss him very much. And for this reason, I will include a few summary results which we have obtained. So it will change the structure of the talk a little bit. Okay, I want to go forwards. This goes like this. So I have planned a little bit longer introduction to show you about pre-Lie algebras, the topics where these algebras arise in a substantial way. You can see here on the lower part areas more from differential geometry, like from affine manifolds, or from affine actions on Lie groups, or from the area of crystallographic groups, so Euclidean and affine crystallographic groups also arising as fundamental groups. And then this here is the title of the talk, so this is today's focus here on Etale affine representations. But yeah, you can see there are also some other areas which are connected with it. For example, in deformation theory, there are some papers people probably know from this area, from Gerstenhaber, about deformations and rings and algebras. And I have seen the word pre-Lie algebra the first time in the papers by Gerstenhaber, somehow mentioning this type of algebra. Whereas in geometry, I saw it first from Wienberg, who talked about, wrote about convex homogeneous cones and somehow introduced these algebras. Yeah, and it's also appearing in physics, operator theory, and Young-Baxter and rotor-Baxter operators. But we will not talk so much today about this. So let me start with a definition. So a pre-Lie algebra, or what is the same, but Wienberg introduced the other name, left symmetric algebra, is like a vector space over some arbitrary field together with a binary operation, so an algebra product, such that you have an identity. And this identity is this one, but what is written here is the associator. So this is like the associator of x, y, and z. And on the other hand is the associator of y, x, and z. So what this means, you have to interchange x and y here to y and x on the left side of the associator. And therefore it became left symmetric algebra because you interchange in this triple, the left part, x and y. Well, this is also a type of algebra which is called Lie admissible. That means usually if you take the commutator, that you obtain a Lie bracket. An important special case is an associative algebra, because then here the equation, the identity just says 0 equals 0. And yeah, then you know the Lie bracket on matrices is commutator. So certainly this will be true. but it actually is true in a more general sense. And this is called readmissible. Some algebras with identities where this commutator defines a Lie bracket indeed, so satisfied Jacobi identity is called readmissible. Okay. Now, there we also use, or from the geometry, there's also the term structure on G. So pre-Lie algebra structure on G. What does it mean? It is that you imagine you have given already a Lie algebra, and on the same vector space, you want to find such a left symmetric product or pre-Lie algebra product, so that these two identities are true. The first one is just that the Lie bracket is the given one you have. And this one, if you replace the first one into here, you see that you get this left symmetric conditions again. So this is the word structure. And the definition then is, sorry, I have to work with the mouse. Then we say, if you have a given Lie algebra, then we say that it admits or does not admit, or it admits a pre-Lie algebra structure if there exists such a structure on this given G. Now let me give 3 very simple examples. Just like I didn't put it on the slides, but I try to explain it. You can, of course, take the Lie algebra GLN itself, and then take this left symmetric product, just a matrix product. Since it's associative, it will certainly satisfy this left symmetric identity. So that's like a very natural example. Or say, take some low dimensional example, take, say, the Heisenberg Lie algebra in 3 dimensions and put the product x dot y simply 1/2 of the Lie bracket of x and y. Then, because the Lie algebra is two-step nilpotent, such an identity is trivially satisfied. And you see, yeah, this also admits a pre-Lie algebra structure. But for a more interesting example concerning existence is you take SL2, say, over the complex numbers or real numbers, and you try to find such a structure. And then you will see that it doesn't work. So there's no structure on SL2 over a field of characteristic 0, and we will prove this. However, if you then have the idea that the field is arbitrary, so maybe has prime characteristic, then you discover, oh yeah, it does work, but then you get the equation 3 equals 0 from the equations if you try it with a basis and then try to find a product and so on. So that's already what I want to say. It depends here on the field maybe. We have an existence question, we have a given Lie algebra, and we want to know if there exists a pre-algebra structure on it. Now, of course, I will explain why you might be interested in this. I already showed you some sort of diagram in the beginning, but we need a little bit of notation. So the left multiplications are here denoted by L of x in this pre-Lie algebra, which has the advantage that now the second identity simply says that this is a Lie algebra representation, which is very nice. And well, instead of representation, you could also simply say module, so that you can define a map L, x goes to Lx, which then is a representation, or G module GL. And the first identity, that xy is a commutator, you could also read this way, that actually the identity map from this vector space to this vector space, which is, I mean, this underlying vector space is the same, is a one cocycle for the Lie algebra homology. So somehow a pre-Lie algebra structure has to do with one cocycles. If I have such a structure, then the identity is a one cocycle. And what is special about this? in fact, is that this map, the identity, is non-singular, so has non-zero determinant. And actually, you can prove rather by an elementary argument that if you have a finite dimensional Lie algebra, that such a pre-Lie algebra exists if and only if there is such a module of the same dimension having a non-singular one cocycle. And you can make this precise how if you have such a non-singular cocycle, you get a formula by sort of conjugation, which gives you then the pre-Lie product. Also here, it would be nice to see a good example. So take here the adjoint module, so the adjoint representation, then this space is just the space of derivations. So in a special case, that would mean if I have a non-singular derivation, then I should have also a pre-Lie algebra structure. And indeed, that's exactly how it goes. So if you have a Lie algebra which admits a non-singular derivation, then you get a pre-Lie algebra structure by a very explicit formula, namely this one. But of course, this puts the next question. If you have this existence question, then you would wonder, okay, how much of a restriction is the existence of a non-singular derivation to my Lie algebra? And yeah, let me tell you what the result is. Jacobson proved in 1955 that over characteristic 0, it's a rather strong restriction. So if you have such a derivation which is really non-singular, then the Lie algebra must be already nilpotent. That's a rather strong restriction. And of course, you're wondering, now if you're like doing algebra and you have arbitrary fields and arbitrary characteristic, what happens if the characteristic is not 0? What kind of restriction do we get by a non-singular derivation, by the existence? And that's also quite interesting. Namely, indeed, the result Jacobson's result really gets false in prime characteristic. And not only that the Lie algebra is not nilpotent, you can even find simple modular Lie algebras, actually of Cartan type, where you have non-singular derivations. So this is work by Benkert, Kostrikin, Kuznetsov from 1995. And it was, why was it studied? Yeah, there were several people working on the theory of pro-P groups of finite co-class, or was a finite co-class conjecture, and Shalev solved it. And yeah, the crucial thing was the existence of non-singular derivations. So this is a special case of pre-Lie algebra existence question. So the general question from an algebraic viewpoint is you have a given Lie algebra and you ask yourself, what kind of structural restrictions does it mean to admit a pre-Lie algebra structure? Okay, let's start with like maybe simple Lie algebras over characteristic 0. That seems to be a rather good idea, maybe even over complex numbers. Then we have a classification, and we should be able to answer this question, hopefully. In fact, it turns out that you can even answer it for semi-simple in a negative way. If the field has characteristic 0, then there is no pre-Lie algebra structure at all. And that was first actually proved in geometry over real numbers or complex numbers with some fixed point theorems and in a language of Lie groups. But later people came up with algebraic proofs. And so because the proof is so short, I will try to give a proof here that for this result. And the only thing which we are using is Whitehead's so-called first lemma. So assume there is such a pre-Lie algebra structure. That means the identity is a one co-cycle with this module of the same dimension as the Lie algebra. Well, by Whitehead's first lemma, because the Lie algebra is semi-simple over characteristic 0, it means the identity is a one co-boundary. But in the language of left symmetric algebras, that just means that there is an element E such that the right multiplication of this element is the identity. However, since we have commutator xy, I mean bracket, Lie bracket xy is left multiplication minus right multiplication, yeah, xy minus yx. That means that we can look at the traces. And since this is a representation, this is a representation, and the Lie algebra is perfect, you know that the traces here are 0 or here are 0. And then that also means the trace here is 0. However, that sounds a bit strange because that would mean that n is equal to 0. And maybe we should say here that we look only for positive dimensional Lie algebras, so that this is a contradiction. Of course, again, the question is, what happens in prime characteristic? And for the first time, as I was trying to look at this question, you realize that somehow the Whitehead's lemma in a prime characteristic is very far from being true, and that it's not so easy to answer what exactly the first cohomology with some modules. I mean, this module is not necessarily the adjoint or some nice module. It could be any n-dimensional module. And then the question is, how do you compute the cohomology? So it turned out that Jens Carsten Janssen gave a very big help for this. So he took up this problem and wrote an article where he computed first cohomology groups for classical Lie algebras. And well, that means for the ones which arise in this existence question for pre-Lie algebra structures, and gave so many technical details that it was possible to continue this question. So actually, we asked him, and he helped us quite a lot by introducing us to this kind of problems. So let me state what then can happen. So in characteristic 0, SL2, for example, has no left symmetric structures or pre-Lie algebra structures, but something can happen in characteristic if the characteristic divides the dimension. And indeed, for SL2, you get the equation 0 equals 3, and then you get really solutions. I told you in the beginning, in this small example, which you might do by hand even, you get some quadratic equations or polynomial equations. Okay, they are a bit hard to solve, but at some point you arrive at 0 equals 3, and then there are solutions. So this is one side, and the other side is what you then can do is in the other cases. Then you can use the Whitehead again, because in these cases, then H1 is really 0. It looks a bit complicated here. I mean, you have to be careful with small primes. Yes. And also for technical, I mean, for some reasons, you need to ensure that you really can compute the first cohomology and that it is really 0. But in these cases, the results of Jens Carsten Janssen are enough to conclude this. If P does not divide the dimension, then we have the same result as in characteristic 0. But if not, it is somewhat open what can happen. I mean, so as far as I know, nobody has classified the cases where P divides the dimension. I have done a few examples which look like that it's always possible to find something. Yeah, but okay, this, as you can see from the year, is very old, so I don't want to tell too much about it. But it is sort of an introduction why in the title we have reductive, because somehow semi-simple is a bit disappointing for this existence question. There are just no pre-Lie algebra structures. So the next case probably you would like to consider is reductive. And that turns out to be our question for today. So again, which reductive Lie algebras in characteristic 0 admit a pre-Lie algebra structure? And for today, we will stay in characteristic 0 here because, yeah, even in characteristic 0, I don't know a complete answer for this. And I suppose that in characteristic P, it will be even worse. So maybe we should first answer the question in characteristic 0. There's one good news. I mean, the Lie algebra GLN, of course, admits pre-Lie algebra structures because the matrix multiplication is associative, and an associative algebra is clearly also pre-Lie, so that is certainly a nice example. But what else could we say? Well, it turns out that this is not so easy. You could be interested in the simple factors arising somehow, and could look if you can say something about it. And yeah, let me perhaps give you already some summary of some results. Namely, you could start in low dimensions, just collecting things and see what you can say. And let me give you a table. Okay, it looks a bit long here, but the black ones are like the ones which are easy. This is GL2, this is GL3, and so on. I decided to go up until, say, dimension 25. So this has, of course, pre-Lie structures because it's GL5, GL4. But the blue ones are something which is not so clear. Although this is here GL4, you have here SL2, and there's no structure. So you cannot just take the direct sum of structures or pre-Lie algebras. You need something else. And actually, I put it into blue color because there's later on in the talk a construction called castling. And with a castling construction, you start somehow from here and can somehow continue it in some way that you get these blue ones. Aha. Then there are some other ones. We see that not only SLN can appear, also symplectic Lie algebra can appear. And the red one is a very particular one, which will play an important role in the second part of the talk. So, yeah, I mean, right now we can't tell too much about it, but you see there are probably constructions where we can have pre-Lie structures. But actually, we don't know if this table is complete, or we don't know in general a classification, or we don't know too much which of these factors can appear. So there are only partial results. Perhaps it's interesting that we get families. So this is GLN. This is somehow you start with an associative product, you have this. Then you can deform this associative product. Actually, that also works. Then you get different structures, not only the associative structure, I should say. This is the castling stuff, which can be prolonged. So you see n plus 1, n squared plus n minus 1. The next term would be n cubed, blah, 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 and so on. So that gets longer and longer. And these are the two special families which I want to introduce today. This is like an SP2N here, and then you have SLNs. And this is an SON, which can also appear. And then these guys. So these two are interesting for many reasons. First of all, to see that there can appear other factors like symplectic or even orthogonal ones. And with these two examples, we also could obtain results which are related somehow in other areas. So we could apply this for other problems. And that's, yeah. So far, the introduction of left symmetrical structures on reductive Lie algebras. Now, you remember, my keys do not work. I can try to get, okay, this is not so good. In the beginning, there was like a diagram where you saw what other areas there are. And oh, let's see, it's with the mouse difficult. So there was also something called affine manifolds, and for that reason, I want to give a little bit of a survey what setting you have in geometry, that you also end up with pre-Lie algebra structures. So here's the affine group, which is a semi-direct product of GLN with Rn. And we can write this as block matrices, where this is the GLN block. Then you have a vector here, and then you have a row 0, 0, 0, 0, 1. And you can multiply these things by this rule. And yeah, this is called the affine group of Rn. And yeah, can be represented nicely by such matrices. So it's a matrix group. And in geometry, there is a very similar group, which is the isometry group of Rn. But here the A is orthogonal. So this is like if you're doing geometry, then this is the isometry group, and this one is a generalization in a bit strange sense, that you give up that A is orthogonal and replace it that A is really just invertible. Well, you have these translations, this part here, so that forms a normal subgroup. And looks in our writing looks like this. And yeah, you need this to say what simply transitive groups are. And the idea is that a group acts simply transitively on Rn by affine transformations. That means you have a homomorphism from your group into the affine group, so that G acts on Rn. And the simply transitively or sharply transitively means there's a unique G that rho G y1 is y2 for all given y1, y2. So this goes back to Louis Auslander, who named such groups simply transitive proofs of affine motions. And he showed by using a standard theory of Lie groups that they are solvable. So this is, again, an already quite strong structural restriction on such groups. We have this normal subgroup Tn of translations. If you want to have an easy example, then that is the case. And next one is, what are affine manifolds or affinely flat manifolds? So this definition is a bit technical, so I just copied it from Milnor's paper, that you have an idea how he wrote this. So the coordinate changes extend to affine transformations in this group. And then if that is possible, if you can find such an atlas where the coordinate changes satisfy this, is called an affinely flat manifold, or for short, just affine manifold. Where the flat has a reason, so I should explain this. So flat means really that there's a torsion-free affine connection, which is, there's an affine connection on the manifold, which is torsion-free and flat. And these two things are algebraic properties somehow, which you can then easily associate to pre-Lie. Because torsion-free means that this connection here satisfies nabla xy minus nabla yx minus xy is 0. So you recognize already, if we put this as a pre-Lie product, this would be the first identity, that xy Lie bracket is a commutator xy minus yx. And flat is that the curvature tensor is 0. This is the curvature tensor here. But again, you see, if we put this here, you get an R bilinear product, and because of torsion freeness and flatness of this curvature tensor, you get a pre-Lie algebra structure. Yeah? So this is the first one and the second one. And if you remember, these were exactly the two identities. So somehow this is a very natural construction from this kind of manifolds where you end up again with pre-Lie algebras. And even more so, there is a third variant, namely that you put into play not only manifolds, but Lie groups. But then you need to consider left-invariant structures. And that just means that the left multiplication maps are affine diffeomorphisms. No, sorry. Should go in this direction. Yeah, in differential geometry, there's the notion of completeness. That's only to understand the theorem better. We do not want to use this right now. So it turns out there is a bijection between this complete left-invariant affine structures on a Lie group and the simply transitive actions by affine transformations, which we have defined with the Ausländer by Louis Ausländer. And everything turns out is pre-Lie algebra structures, more or less, up to suitable equivalences maybe. So these things correspond. So these structures on the Lie group, you can pull down to the Lie algebra level and you get exactly, again, these pre-Lie algebra structures. Well, the simply transitive affine actions are a little bit stronger. There you get a complete one. And what means complete on the level of the Lie algebra? It means here's some sort of characterization. If all right multiplications are nilpotent, that's actually, you have to justify the definition that it really corresponds to the completeness in the differential geometry setting, of course. And here's a paper where this existence question of pre-Lie algebra structures really comes from. And you see the titles fundamental groups of complete affinely flat manifolds, so these affine manifolds. The paper is in 1977 and asks you existence question for a given solvable one. So does every solvable n-dimensional Lie group admit such a complete left-invariant affine structure? And the algebraic version is, because you really can just pass to the Lie algebra, and then you get a bit more general question because you can extend it to characteristic 0, of course. You can also consider it with or without complete. So, but the question is, like, if I give you any solvable Lie algebra, is it true that there is a pre-Lie algebra structure on it? This is for solvable. And just to present a little bit of history, the answer is no. And certain counterexamples have been constructed, in the first one by Yves Benoit. And already on the level of nilpotent Lie groups and nilpotent Lie algebras. But I don't want to be too long on this section because, yeah. But one tool is very important. If you're working on the Lie group, you want to transfer these properties as much as you can to the Lie algebra. And this left-invariant affine structure has one interesting consequence, namely that your Lie algebra admits a faithful representation of a rather small degree. Why small? Well, this is n-dimensional, and this is n+1 dimensional, and it should be faithful. It turns out that this is often not possible for some Lie algebras, cannot be represented in such a small, with such small matrices. Yeah, and these, like, is the idea that you get a negative answer by showing this, that somehow certain Lie algebras cannot admit such a faithful linear representation at all of small degree. The proof here is rather terrible because somehow you have to classify all the other representations and show they are not faithful anymore. That's not so easy, and there are no really canonical techniques to do this. So you really have to work hard for this. And I mentioned this because I told you about Wolfgang Mohn's work with me. He did a thesis on Ardo's theorem. So actually, you can formalize this by asking what is a minimal dimension. And it was known already for a nilpotent Lie algebra, which is k-step nilpotent, say, on dimension n. You get some exponential bound, mostly like this. Ardo's theorem itself, if you look at the proofs in the books, usually you have an iteration n times this dimension n. So n to the n is the bound usually there you would get is even worse. So you need to do some improvement. And that's then what Wolfgang did. And we arrived at some results making this more precise. So this is then here, for example, the Neal radical. So this is a reductive Lie algebra where the mu is known and the difficult part still is somehow the solvable. If this is solvable, so you can assume here R is at least 1. So then you see that you can't get rid of this term really. And even in this case where you fix one dimension, it is rather hard to determine what the mu exactly is. We can only say, I mean, n plus 1 for 10 would be 11. So everything which 12 or more is a counterexample for Milnor. And we can prove that the worst case which can happen is 18 by really considering portions of the universal enveloping algebra and careful studying chains in it. So it's very complicated, but we cannot answer what exactly is a mu. We can only give a bound. So that's still very complicated, but Wolfgang did a lot of work for this. And yeah, oh, that was very quick. So I apologize for a rather long introduction, because now finally I'm arrived at the Etale affine representations. But yeah, I thought it would be maybe interesting to explain a little bit the motivations you have. So they are from geometry, but also from algebra, and interest in modular Lie algebras, even simple modular Lie algebras somehow is involved in it. For reductive, you can do something else. And therefore, we need the Lie algebra of the affine group, which is then the affine Lie algebra. So V could be Rn here, if you want. But actually, what does Etale mean? It means that the evaluation map, here is an isomorphism of vector spaces. So in particular, the dimensions are equal. And if that's the case, such a vector V or point V is called a generic point. And again, this is nothing else than pre-Lie algebra structures again, just in a different angle of view. Why is that? I mean, I don't want to give a long proof. I just want to give you an argument. Why is it the same? Given such an Etale representation, you get a pre-Lie algebra structure by this evaluation map. This is a linear part of this block matrix of this affine Lie algebra. Here, this is the GLN block, and the vector, the Lie algebra doesn't have a 1, but a 0. So that's one way. And then also in the other way, if you have a pre-Lie algebra structure, you get an Etale affine representation. Okay, we can normalize it to the point 0 if you want, and then this is the Etale representation. So actually, this is just a fancy way of talking again about pre-Lie algebra structures. Now, what we can do now is we look at rational representations of complex, it's easier for us, complex algebraic groups. And there's also the notion of an Etale affine representation. And that's probably a good setting, because then you can take the Lie algebras here. That is at least something. It's not every Lie algebra is the Lie algebra of an algebraic group, but still, it's a very good idea to do this. And the definition is, we call it Etale affine if there exists a point in the space such that the orbit rho g applied to V is Zariski open here, and the stabilizers are finite groups. And what you can do then is you can take the differential and you can show that this gives you a pre-Lie algebra structure on your Lie algebra. So Etale affine representation of the Lie algebra. So working in this area gives at least examples of pre-Lie algebra structures here. Now, there is something called prehomogeneous representations or prehomogeneous vector spaces, and it turns out that we can use this. This is rather surprising, perhaps, but this prehomogeneous... Sorry? What did you say? I have problems to get out here. Can you say it again?
No, I think it was nothing, just some microphone open. Oh, busy. Go ahead.
Oh, I'm sorry. I have problems with this presentation mode. I cannot leave it anymore, but okay. I hope you, please tell me if you can't see me or can't read, then I will try to reboot or something.
It's okay.
If not, okay, then
everything is okay.
Okay. Okay, I apologize that I need a few words here. So we are now in the reductive case. Also, we want to look at reductive groups and reductive Lie algebras. And there's the word regular. And that means for the V's, which are not just in the singular set here, yeah, which is the complement, then the stabilizers should also be reductive. Yeah, this is like a condition for your Lie algebras and the stabilizer Lie algebras. And actually, these Japanese people have studied these situations. One has to be careful with the names. If you interchange S and K, you have Kato Shimura, and that's number theory. But no, it's Sato Kimura, and they work on these algebraic groups and with these prehomogeneous representations. And this regular means that each isotropic subalgebra here is reductive in. And this reductive in means they are not even reductive, but also the adjoint representation of the subalgebra on the whole Lie algebra is completely reducible. So it's a bit more than just being reductive. Yes, it's a bit more of a condition. And we don't need this really, but the people speak there of relative invariance and absolute invariance if you have non-zero functions, which for a character, which is a homomorphism to the multiplicative group, satisfy sort of invariant condition. And this prehomogeneous condition can be formulated also in this way, that these invariants are constant. So I only want to say this prehomogeneous has been studied by many people, so we can use it. And if we have a reductive group, we have another thing which gets a bit easier, namely this homomorphism into the affine group can be replaced by a representation into the linear group. So we can, instead of F of V, we can work with GLV. And this is make things much nicer for us, yeah, because we assume from now on that our group is reductive. Then we say the following, and now we have these two very important words for us, namely Etale. We defined this already, but now we can make a better definition because we may assume from the beginning that we have a linear representation, so from G to GLV, from a reductive group. And Etale means simply that this rho of G has an Zariski open orbit and that the dimensions are equal. And we write this usually in triples, like you have your reductive group here, then you have the representation, and this is the vector space GLV you're here. And these triples are somehow the ones we have to study. And you remember these isotropic groups should be finite. But what if they are really not only finite, but trivial? That is a subcase, and we didn't know any better word, but we called it super Etale because then things get even better for the whole study. And what you get is always a regular prehomogeneous representation. So this is the key result, that our problem on pre-Lie structures reduces to a regular case of prehomogeneous representations studied by other people. So we can take a special case of them. So this is a point. And from the prehomogeneous setting, there was something known as castling. And castling somehow means you start with one which you already know is prehomogeneous, you make it larger, and then the castling transform is again prehomogeneous. And that also works for Etale. So you can make it longer or bigger, and you get more examples once you have an example. The technical details are not so important for us here. We can even work with SLN here instead of GLN. So maybe this is only a formal definition. What I want to say is, let me make one example where you can see what I mean. Here, imagine you start here with GLM. GLM has an associative product, so it has a left symmetric product, so it has an Etale representation. And then you trivially extend it by the trivial group SL1. You do this castling, and you get this factor here, and that's again Etale. You do it again, doing this setting, apply it recursively, you get the next one. Yeah, and that's what you saw in the beginning in this table, where you get somehow GLM, then that which is SLM times the one-dimensional stuff. Then m-1, m squared minus m-1, and then it goes on. Oh, I was wrong with the cube. The next time is degree 4, so m4 minus blah, blah, blah. And this gets worse and worse. Yeah? So, but this is known. So what people then do is they say, okay, since we can go infinitely further here, a classification of these things is impossible except you mod out these castling transforms. So any reasonable classification is only up to castling equivalence. And that's clear why, because that gets worse and worse and you don't want to have this. And you can do this. And then you see that these people here have classified this according to whether the prehomogeneous representation is irreducible, or if it's not, you have a problem with the number of factors, and the people were only able to classify it with like at most 3 simple factors, and after that they gave up because it's too hard. But at least you can use something of it, and that's what we did. If you look for Etale, which was stronger than just prehomogeneous, yeah, we had more conditions. It's rather, for irreducible, it's rather a nice, because we only have 3 cases. But then this representation is irreducible, and nobody said it must be irreducible. But if it is, you get a very good classification. So the pre-Lie existence question, or the Etale thing for irreducible ones, is just these 3. Yeah, from GL2, we knew this beforehand, of course. And then you have these 2 other cases. Okay. But if it's non-irreducible, and then you have 1 simple factor, you still get a reasonable classification. But yeah, you see, we should stop very soon, because if it gets more, it gets worse and worse. So that will be impossible. So let me summarize what was known. So I've worked ages ago, you see, a very long time ago. The first result which I had there was, if your S here is simple, and you have this here an Etale representation, then it can only be SLN. That's already interesting. Yeah? All the other simple factors in such a way which only one summand one factor cannot appear. That's rather surprising. And 20 years later, Wolfgang Globke, a student of Oliver Bauer's, made a thesis where he showed, for example, this one, that you cannot continue with another SLN. And then Wolfgang Globke became my postdoc, and we worked a little bit more on this and discovered, okay, that's not only for SLN. You can have whatever you have here, k times, at least 2, because if it's only 1, then yeah, it can be only SLN, but otherwise could be more. But that can also not happen. Aha. That's also interesting. And let me, because of time reasons, let me skip the proof of this one here. So I have a version where I have a proof here, but somehow it's good to know if you have one-dimensional center. That's a very good case. If the center is one-dimensional, you can say more. If you have an Etale representation, you have a proper subrepresentation, then this proper subrepresentation cannot be regular. So then these stabilizers are not reductive in the other one. And that's somehow very good to make progress in these questions. And I have a proof, which I only do if I have enough time, where you can see it's using some Rosenlicht formula, but this is all well known. I'm not an expert in this area anyway, so I had some trouble to write a nice proof, but let's continue with something else. Yeah, an example. Well, yes, it's non-regular then. For if you take matrix multiplication, you can see that this is indeed not the case then. And let me continue to, after we had some results, some other people ask us, oh, well, are you aware of this result and this result? So let me introduce, and this is a very technical thing, but I need to know what special means. So special group means that the factors are, if every maximal connected semi-simple subgroup is isomorphic to this here with SLNs and SPMs. And why has this to do with our problem? Well, Popov had a paper on linearizable subgroups of this affine Cremona group, yeah, which is like an infinite dimensional algebraic group, and the Lie group is called Jonquière group, the counterpart. And he said, in our language, the following, namely that reductive groups having a super Etale representation, so there were the stabilizers even trivial, is special, must look like this. And what we did was, first result is, can you extend this to Etale actually? Is it true for Etale also that then this group must be special? And the first result we have here is already a few years ago, but I thought it is still interesting perhaps. No, you cannot. This is the red example from the table in the beginning. You can construct families of Etale representations so that the group is not special. Yeah, the SON here is not allowed. You remember there were only SLNs and SPNs, but not an SON. That can't be. So the group cannot be special. So this cannot generalized. But even more so, Popov said he had a conjecture telling that if you have a super Etale representation, it must be GLNs. And well, that's probably now the point of our whole paper. There we found counterexamples. So that's actually not true, because you can have things here with a symplectic group. Okay, the rest is GLN, but here you can add a symplectic groups and you can prove that there are really super Etale representations. Again, the proof, I don't want to bother you with the proof. You have to compute a lot, even to compute the right dimension is something. If you have such a terrible formula here with transposed matrices and so on, okay, the dimensions must be equal. Then there must be the generic stabilizer must be trivial. you do some sort of induction to see that it is really trivial and that is a super Etale. Here I write the step is more involved just to save time because yeah, it's rather long. I'm not really able to do this. And then you see, okay, the dimensions are the same. It has an open orbit and that the open orbit map, this orbit map is G equivariant open embedding. So that is enough to prove what we need. And that has, to come to the last 5 minutes, that has a rather interesting application, which we didn't know. So then these people working in this area told us, do you know the Zariski cancellation problem? And we said, no. And then, okay, we looked it up. So this seems to be a famous problem in this area that if you have affine varieties x and y, and you know that y and x times y are isomorphic to affine spaces, a to the s and a to the s plus s. Can you cancel it? But x is not isomorphic to an affine thing. Is that possible? And I think for higher D, that's completely unknown. This has a local version where you first need the word flattenable. Flattenable means that X is isomorphic to an open subset of an affine space. So here we have these affine spaces. And the local version is then, can it happen that you have affine varieties X and Y such that Y and X times Y are flattenable, but you cannot flatten X itself? This is the same as here, more or less, but in a local way. It has this name. And we could prove without knowing it, but it gives it that actually the local one is true because you see exactly we take X as the symplectic group and Y this direct product of GLNs. And flattenable means super Etale. So we have that, but X itself is not flattenable because a semi-simple algebraic group has no Etale representation. That's the same as the Whitehead proof you saw, right? Because the Lie algebra then, because of Whitehead, has no pre-Lie algebra structure. So semi-simple cannot happen. That's exactly our proof from the beginning, which is very elementary, but it gives you, yeah, that the local Zariski cancellation problem, the answer is affirmative, that can happen. All right. So Popov has words which I don't want to explain too long. You can call an algebraic, he calls it equivariantly flattenable with left multiplication, so that his problems are the same as ours. So his language is obtain a classification of equivariantly flattenable reductive algebraic groups. And our language is obtain a classification of reductive groups admitting a super Etale representation. That seems to be an open problem. So we have made a few results, but we are far from any classification or more. And this is then even worse because instead of super Etale, it's Etale. Yeah, and that gives, if we pass to Lie algebra, then you get, of course, pre-Lie algebra structures on reductive Lie algebras. However, there's a further problem which I don't know how to answer. Is it always the case that all pre-Lie algebra structures are algebraic in the sense they arise from a reductive algebraic group in an Etale representation? I haven't found any. I mean, I'm not sure. Probably this is not the case, so that this problem might be even more complicated. Okay. Thank you very much for your patience. I hope it was not too long, but at least I'm in time. So thank you for listening.
Thanks, Dietrich, for your excellent talk. Are there any questions, comments, or remarks? Yes, please.
I have a short comment. Thank you very much for a very interesting talk. Just a remark about cancellation problem. You said that it looks completely open for big values of d, but in fact it is open even for d equal 1. Starting from dimension 3, it is unknown. There is a counterexample in positive characteristic due to Nina Gupta, but in zero characteristics, this is open for d equal 1.
Oh, okay, already for d equal 1. Yeah. So I'm no expert, so I just read that higher d is probably completely open, but even smaller d. Okay, yeah. Yes. Thank you.
Any other questions? Okay, if not, let's thank the speaker again.
Thank you.
Okay, thanks. We will resume next Monday at the usual time. Bye, everybody. Have a nice day.
Thank you. Bye-bye.